The Duracell batteries we make now live longer than the ones from a few years back.
Ever wonder how companies can make claims like this?
Today's Duracell lasts up to 30% longer.
At companies like Duracell, or here at Kodak's Ultra Technologies, marketers back up their claims with rigorous testing. A sample of batteries is run to exhaustion. It's a basic statistical procedure. To estimate some characteristic of a population, a sample is studied and estimates are made based on that sample data. Estimation is one type of statistical inference, the science of drawing conclusions about a population on the basis of sample data. We'll see in this unit that there's more to statistical inference than just guessing. Confidence intervals are the tool we need to give a really useful estimate.
Just going to take your blood pressure.
Like all statistics, confidence intervals start with individual observations, like a measurement of blood pressure. Will Shaw visits his doctor for a routine physical exam.
And one of the things, of course, that causes blood pressure to go up is when a person's nervous.
That's what I am, nervous.
Right.
But Will's blood pressure is actually going down.
Well, it's interesting. Your blood pressure's come down. It's 160/80, and that sort of thing happens all the time. A lot of people think that blood pressure is constant. It's the same all the time, but it isn't. It varies.
The reading involves two numbers.
That first number is the highest pressure in the blood vessels, and the second number is the lowest pressure in the vessels.
Say this is Will's blood pressure reading. Because blood pressure varies, a single observation isn't enough. We need an average of several observations. The higher of these numbers, the systolic blood pressure, is the one we'll use for our average. We'll take a reading once a day for a week. Here are the remaining 6 measurements. The mean for this sample is X bar is equal to 1 over the number of observations times the sum of all the X values. When we make the substitutions, we get a sample mean X bar of 130. Think of all of Will's blood pressure readings as the population. We want to estimate the mean of that population, which we call mu. Because the sample mean is 130, we estimate that the true mean mu is also 130. But how accurate is this estimate? After all, we already know that sample means vary. If we repeat the same process next week, the sample mean probably won't be 130. Well, in statistics, there's a way to figure out just how accurate an estimate is. To get at this, we start with some assumptions about how Will's blood pressure behaves. First, the measurements have to be far enough apart in time that they don't influence one another. In other words, they are independent observations. Second, we assume that as Will's blood pressure varies from day to day, it follows a normal distribution. What we want to estimate is the mean mu of this normal distribution. Third, we'll assume we know the standard deviation of Will's blood pressure distribution. It's 20 points. Usually, we also want to estimate the standard deviation from data. But here, where we're interested in the broad ideas of statistical estimation, it's simpler to assume the standard deviation is known. The problem with using X bar to estimate the unknown population mean mu is that X bar varies when we take repeated samples. The solution to the problem rests on the fact that we know just how X bar varies. We know that the sampling distribution of X bar is normal. The mean of the sampling distribution, the mu of X bar, is the same as the unknown mean of the population, mu. And the sample mean is less variable than individual observations from the population. We also know that the variability of X bar is described by its standard deviation, sigma of X bar. This is the familiar formula for figuring it out. Sigma of X bar is the population standard deviation sigma divided by the square root of the sample size. In this case, sigma is 20, and the sample size n is 7. So sigma of X bar is about 7.6. Now recall the 68, 95, 99.7 rule. In any normal distribution, 95% of the observations lie within plus or minus 2 standard deviations of the mean. That's true of X bar as well. 95% of all possible samples give an X bar that lies within plus or minus 2 standard deviations of the population mean mu. Since in our case the standard deviation of X bar is 7.6, 2 standard deviations is 15.2. With this information, we can begin to make inferences about Will's blood pressure. The population mean mu is unknown, but we do know that 95% of all samples that we would ever take have an X bar that is within plus or minus 15.2 of mu. This is the same as saying that mu is within plus or minus 15.2 of X bar. Here, X bar was 130. So we can say that we are 95% confident that mu lies within 15.2 of our X bar. That's 130 minus 15.2, or 114.8, and 130 plus 15.2, or 145.2. This interval, X bar plus or minus 15.2, is called a confidence interval. Any confidence interval has 2 parts. The first part, as we've just seen, is an interval obtained from the data. In our case, the center of the interval is the original estimate, the sample mean. To that, we add plus or minus 15.2 to indicate how precise the estimate is. We call 15.2 the margin of error. The second part is a confidence level, the probability that our method will produce an interval that contains the true mean mu. The confidence level tells us how well our method will work in the long run. Think of the interval as a net. Each time we take a new sample, we throw the net again. Sometimes we catch mu, and sometimes we miss it. Here's the interval from one sample. It contains mu. Here's a second, another catch, and a third. That one missed. We can never know whether a particular X bar, like the one we came up with for Will's blood pressure, is a hit or a miss. But we do know that as we continue to take samples, we will catch the true value of mu 95% of the time. In other words, the probability that the method works is 0.95. So when we say that we are 95% confident that Will's blood pressure lies between 114.8 and 145.2, we mean we got this interval by a method that works 95% of the time. When battery companies like Kodak's Ultra Technologies test their products, they choose in advance just how confident they want to be in their results.
When we're creating a confidence interval, there are many things that we have to take into account. One, we have to see that we have a normal distribution. We have to have representative samples of the product.
Random samples of, say, fresh AA batteries are pulled from the warehouse. Then it's time for the rack, a device from which no battery emerges alive. Here, the batteries will be drained of their juice under controlled conditions. Although the rack is quiet about it, it's mimicking the load of real products, such as toys. So if the object is to see how long the batteries last in products, why not use the actual toys themselves?
Batteries are not particularly an interesting product. You'll see use of toys in commercials. The testing that substantiates those claims wasn't actually done in real toys. You'd have the variable of the life of the battery, but also the variable of the performance of the toy.
As the batteries continue to discharge in the standard test, a computer turns them on and off in cycles to represent the consumer's typical use pattern. Battery voltage is constantly monitored because just as in real toys, there comes a time for all good batteries to run down.
The computer will compile for you the mean value, the standard deviation of that data, and you can go ahead to the final step of creating the confidence interval with that data. The parameters you need, of course, to calculate that are the mean, the standard deviation, and the sample size, and your choice of what confidence interval you want. And what we can report in our engineering report is that this population of AA batteries, when used in a toy, can be considered to last 7.5 hours plus or minus 20 minutes, and our confidence in that range is 95%. Our management can go ahead and make decisions based on that confidence level.
A confidence interval allows us not just to estimate a parameter like mean battery lifetime, but to say how accurate the estimate is by giving a margin of error. We can't be absolutely sure of this accuracy, but we can be as confident as we need to be. Kodak is happy with 95% confidence. But if that's not enough, 99% confidence could be arranged. We would use a method that catches the unknown population mean 99% of the time. Before we can understand what's involved in choosing between confidence levels, we need a general recipe that works for any confidence level. Let's start with 95% confidence. The margin of error is about 2 standard deviations wide, because going out 2 standard deviations from the mean of any normal distribution catches the central 95% of the outcomes. We need to find the z-value that corresponds to this area. We call this z-value z-star, and we find it in a modified version of the familiar z-table. The table shows the z-star values for several different confidence levels C. For 95% confidence, the table gives z-star equals 1.96. That's a bit more exact than the 2 we get from the 68, 95, 99.7 rule. So the margin of error extends 1.96 standard deviations on either side of the estimate x bar. Because the standard deviation we're talking about is that of x bar, which we already know is sigma divided by the square root of n, the recipe for a 95% confidence interval is x bar plus or minus 1.96 times sigma over the square root of n. But what if we need 99% confidence? Well, this confidence interval is based on the central 99% of a normal distribution. The table shows that the central 99% of any normal distribution lies within z-star equals 2.576 standard deviations from the center. Now the margin of error extends out 2.576 standard deviations from x bar. So a 99% confidence interval is x bar plus or minus 2.576 times sigma over the square root of n. Here's the general recipe. For any confidence level C, look in the table to find the corresponding z-star. This is the confidence interval. Here, x bar is the basic estimate of the unknown population mean mu, and this expression is the margin of error. With the z-star values in hand, we can find our confidence interval by simply plugging in the appropriate numbers. And let's say we want a 99% confidence level on the estimate of the average lifetime of a battery. The sample mean from tests is 360 minutes. The z-star value for 99% confidence is 2.576. The population standard deviation is 23 minutes, and n, the number of batteries tested, is 40. Doing the arithmetic gives us our answer. The true mean will fall in the range of 360 minutes plus or minus 9.4 minutes in 99 out of 100 samples. This recipe helps us understand some important facts about the behavior of confidence levels in general. First, higher confidence is not free. There's a trade-off between confidence and the margin of error. The cost of higher confidence is a bigger margin of error. A 68% confidence interval has a margin of error that extends out about 1 standard deviation on either side of the mean. If we want 95% confidence, we must go out about 2 standard deviations, and so on. In the recipe, the confidence level determines z-star. As the table shows, higher confidence demands a larger z-star, and so a larger margin of error. The recipe shows that the margin of error also varies with the population standard deviation. The larger sigma is, the larger the margin of error. And that makes sense. The more variation there is in a population, the harder it is to pin down the mean mu. Changing the size of the sample also affects the margin of error, but this time it's a factor a researcher can control. For a given population, sigma is fixed. At a given confidence level, say 95%, we also have a fixed z-star. Because the standard deviation of x bar is sigma over the square root of n, the margin of error gets smaller as n increases. More data points give us more information and enable us to estimate the population mean more accurately. We can get a margin of error as small as we want for any confidence interval just by taking enough observations. But a larger sample size is more expensive. Users of statistics have to balance how many observations they would like against how many they can afford. And that square root in the recipe makes matters worse. To cut the margin of error in half, we must take 4 times as many observations. In this unit, we've learned a lot about estimation, a type of statistical inference. We learned how to estimate the mean of a normally distributed population. If we were estimating a different parameter, or if the distribution of the population were not normal, we would use a different recipe. But what's important is that the basic logic we've learned here would remain the same. We've found that a confidence interval not only estimates a population parameter, but gives us a margin of error and says how confident we can be in the result. We know that there's a trade-off between high confidence and a small margin of error. We've learned that increasing n brings down the margin of error. And we've also learned the specific recipe for this very useful confidence interval.